also with the recording for this meeting. And I will also share my screen. I hope you can see my screen. If not, let us know by typing something into the chat window. So please, again, I welcome you. I would like to take this opportunity to welcome you to this webinar. It is the second webinar of this series, introducing a new ATENA version 5.7. This version is now available for downloading from our website. But I want to remind you, before downloading it and installing it, please check your maintenance. It is only, it will be working for you only if your maintenance is active. That means more exactly if it was active at the end of August. So this, the previous webinar was focused on the durability model. This webinar, I want to focus on the reinforcement modeling and the modeling of prestressing. Of course, this is not totally new in ATENA. ATENA from always was about reinforcement modeling, but we have now improved slightly the possibility for prestressing modeling. So I would like to go through that. I think it is always good to remind ourselves and give us some more detailed, give you some more detailed insight into the modeling of reinforcement. Also, we have some persons which are new in this webinar or new to ATENA. So please excuse me if I will be repeating some of the basic topics some of you may already know. So something about our company for the new people in our webinar today. So we are located in Prague, Czech Republic. This is the famous building in Prague, which is the Prague Castle. And that's our office is actually not far from this building. So if you walk from our office to the Prague Castle through this park, this is actually the view that we see. So we are a small company, but very much we are trying to be very internationally active. So we are selling the software all over the world, and we also provide various consulting services in many countries all over the world. So what we do, we focus, as you may know, or many of you, we focus on modeling of concrete. So we try to develop technologies and software tools that allow engineers to simulate realistically the behavior of reinforced concrete structures. So by that, I mean that we create a finite element model, we simulate the structure, and we can model its behavior, taking into account the cracking, as you see here at this nuclear containment vessel, and all the way up to, we increase the loads all the way up to structural failure. This gives an overview where our software is being used all over the world. And now let me summarize some of the new features which are available in the version 5.7. I would say the most interesting feature available is this durability model. We discussed that in the previous seminar, which was in August. So if somebody is interested, you can find this recording of that meeting on our YouTube channel. So there we can simulate the chloride ingress into the structure or the carbonation. And as you know, the main effect of these ions or these chlorides propagating or carbonation into the concrete is the reinforcement corrosion. Another new model is the alkali-silica reaction. That means this is the reaction between the aggregates and the contents in the concrete, in the cement, which causes the expansion of the aggregates. which causes microcracking and basically degradation of the material. Another new elements is and features is the further improvement of 1D beam and 2D. Sorry, there is a mistake, not 2D beam, but 2D shell elements. As you know, in the past, we used to have 3D beams. That means you model beam as a 3D element. But because it is sometimes tedious to model everything by 3D elements, we have introduced also 1D or standard equivalents such as 1D beams and 2D shells. And then it is the main advantage of these elements is that you can create very complicated global models where some parts can be modeled by beam elements and some parts by solid elements. So we have also new let's say, elements or new conditions how to connect these various elements together so that we can combine or create complicated models where some shear parts or more details can be modeled by solid elements and the rest of the structure can be 1D beams or 2D solids or 2D shells. For also, there are improvements in the construction process modeling.
So much time to connect the audio to my...
I'm sorry, there was some question. So I again repeat, please mute your microphones. And if you have any question, type it into the chat window. Let me check, because I don't see the chat window now. Okay, there's nothing there. So let me continue with my presentation. And another important new feature is the increase, or actually increase in speed. Yes, it should not be increase in analysis time, but it is increase in speed. Yeah, it is analysis time and post-processing speed. So this is mainly the processing of reinforcement, how the reinforcement is being attached to the solid materials. This has been improved. So the analysis time can be sometimes even 3 times or 4 times faster than in the past version. Just to give you a summary of the material models in ATENA, this is mainly for those who are new to ATENA. So ATENA is mainly for concrete. So our main material is this fracture plastic material model, which is using Menet-Revelam criterion in compression, non-associated flow rule. And this plasticity model is combined with the fracture model using the smeared crack approach. For soils and rocks, we have a Drucker-Prager model. There are also interesting and modern materials based on the microplane theory of Bajant. For steel, we have the von Mises model. And we also have time-dependent models for heat and moisture transport, for fire analysis, creep. Now this corrosion model is available, and dynamic analysis. Short summary of the basics of the material model. So this concrete model is using this 3D criterion, as you see on the left. And it is combined with a cracking model to simulate this crack opening claw, as shown on the right, where the softening claw controls the release of energy during the cracking process. Well, we always validate our models based on experiments, but the best validation is always these blind predictions. So I like to just give this summary that we participate quite often in these predictions. And mainly I like these results, as you see here on the bottom left, which was done by Dr. Uyl from Delft, and he received the first place, I mean, the best prediction for these pre-stress beams. And maybe one latest one, I already showed it last time, but for very briefly go through it. This was this test by Toronto, very large test, and ATENA obtained quite good predictions. So actually this test consisted of two tests. First they loaded the beam and it cracked and failed on the right side. Then they strengthened it, continued with the test to fail also the other side, which was with shear reinforcement. This right side was without any shear reinforcement, so that's why it failed, collapsed first. And we obtained very good predictions. This was a blind prediction. Here you see these results. The dots in the red circles, those are predictions by ATENA. And we were always in this yellow zone, which was, so to speak, 10% zone of fame. But of course, we have to acknowledge that some luck is involved, because from our uncertainty modeling, we know that typical uncertainties in shear problems in ATENA software are about 16%. Well, one more thing I also want to point out, one of the new development, it is also possible to use ATENA on the cloud. If you go to this website, ATENA Cloud, cervenka.cz, you can obtain an account there, and there is some initial free period. You can try ATENA. This may be interesting for the first-time users who want to try ATENA. But it may be also interesting nowadays that many of us have to work from home or are not able to go to the office. So this cloud version can be used to run nonlinear analysis or ATENA analysis remotely. All right, so let me now go to, this is again, yeah, I forgot to mention, this is the window you obtain when you connect to this cloud service, and there you can select, this is the kind of a selection dialog where you can select which kind of program you run. Or there is also access to the documentation and examples. So let me now go to this reinforcement modeling. So let's basically summarize how ATENA model reinforcement. So in ATENA, we can have very detailed model of reinforcement if necessary. That means each reinforcing bar can be modeled. It can be straight, it can be curved. And then we can perform nonlinear analysis of this. Well, the other, let's say, interesting features of ATENA is that during the analysis, you can see what's going on. This is on the left bottom. This is the typical window that you see when ATENA is running. That means you see the development of cracks, but you can define some monitoring points and follow the curve, which in this case is a low displacement curve, but it can be, for instance, the strain development in reinforcement or maximum crack width evolution. So that's why we call it virtual testing. And on the right, you see the typical crack display from ATENA. You can see the cracks on the surface, but also, if you like, you can see the cracks here. So let's summarize the models we have in ATENA for reinforcement. So we have basically two models. One we call smeared reinforcement. That means you model the reinforced concrete as basically a composite material consisting of reinforcement in various directions, just defined as a reinforcement ratio and a concrete. So this smeared reinforcement approach is, of course, good for cases when you have a lot of reinforcement and it would be very tedious to model each bar separately. So one possible case would be, for instance, if you have a lot of ties or a lot of stirrups in a beam, those ties or stirrups can be modeled by this smeared reinforcement. But let's say the most popular and most accurate model is so-called discrete model. That means each bar is modeled separately. In that case, we have separate model of the solid elements, which in this case is a 3D element, and then we have reinforcement passing through these elements. So in ATENA, this is defined totally separately. And let me show how this is done. So imagine we have this kind of three surfaces through which define our model, which is maybe this some kind of corner. And we have a reinforcement, which is this blue line passing through. So this is defined totally independently. And then we create a finite element model. Now this is, let's say, connected to our preprocessor GID. In the GID, you have to always run the meshing, and this then somehow meshes these three surfaces to create quadrilateral elements. And through that is passing the idealized reinforcement. Now you see the reinforcement, which initially was curved, is somehow idealized by linear segments. And this selection of these segments should be such that it sufficiently estimates or models the reinforcement direction. So then this information, when we start ATENA analysis, this information is sent to the program, and the program makes further refinement. The program then searches how this reinforcement definition intersects with our, in this case, 2D mesh. And at each intersection, it puts a new node, new reinforcement node, which is indicated by these blue points. And also it adds one truss element representing the reinforcement, connecting these blue points. So in the end, we have a solid element, and inside this solid element, we have embedded truss element representing the reinforcement. This is similar to the, sometimes this is called embedded reinforcement. But in ATENA, this reinforcement stiffness, let's say, or reinforcement element is not embedded inside the 3D element, 2D element, but it is done by a displacement constraint. So we constrain this displacement of this reinforcement node. These displacements are indicated by UR. We define a kinematic constraint, defining how this displacement is connected to the displacements of the surrounding 3D nodes. So we have this equation saying that the displacement to UR is a linear combination of these UI displacements. And these alpha factors are calculated from the element shape functions. So this is how these two models are put together. And another important thing is that with this condition, with this kinematic constraint, this basically defines a perfect connection. And we know that in reinforced concrete, this connection is not perfect between concrete and reinforcement. There may be some bond failure. So, of course, if we have a sufficiently fine mesh, this bond failure can be simulated by the cracking of surrounding elements. Because in typical reinforcement with ribs, the bond failure is nothing else than cracking of surrounding concrete. So if we have a sufficiently fine mesh, this bond failure can be actually quite well represented by cracking of surrounding elements. But in addition, in ATENA, we have the possibility that we also take into account this bond directly. And this is done by adding additional degrees of freedom to these reinforcement nodes. And this additional degree of freedom represents slip. And then we can directly use a slip law to given in the codes or measured in the laboratory to simulate the bond failure between concrete and this approach gives us also another possibility, which I will show in the next part of my presentation today. We can also use it to simulate pre-stressing losses. So this will be covered by my next part of my talk today. I forgot to mention that at the beginning, but first I wanted to give this presentation, and then I will show the program and show one example of this pre-stress of modeling of pre-stressing, where we will use this slip, these special elements with the slips to simulate, first of all, losses during pre-stressing, and then also to simulate reinforcement bond after the cable is injected. There is some question. Let me see. That window. Yes. Okay. So there was a question. First question from Ansi. Hello, Ansi.
Hello, Jan.
Nice to having you to joining this webinar.
Yeah, thanks. It's very good to be here.
So the first question was, what kind of calibration of models has been conducted, basically related about structural analysis? Well, I showed some analysis from some blind prediction competitions, and those were usually shear kinds of problems, or yeah, usually they are shear because that's what people find more interesting or more difficult. But of course, we use also more simple problems for our calibration, bending, compression, and so on. Yeah, if there is time, I can show some of them also. We are doing something now for the calibration of the safety format.
Yep, thanks.
Non-linear analysis, but maybe you can talk about it also later.
Yep, that's okay.
Then about the bond models, yeah, you mentioned crack spacing and tension stiffening. Yeah, yep. Basically the bond model, the bond together with, well, as I said, usually the bond failure in concrete is by cracking or crack development in the surrounding concrete. And this, of course, is very much dependent of the crack spacing as it evolves, and kind of the consequence of this process of crack development around the reinforcement is the tension stiffening. So what we are finding is that if you are using sufficiently fine mesh, then just by good concrete cracking model, you can recover tension stiffening automatically without the need to put any special features into your model.
Okay.
On the other hand, this is dependent on sufficiently fine mesh. Yes? If you are modeling a bridge, maybe you cannot go into such details.
Yeah.
So in that case, we have the possibility to define the crack spacing. If you are using very large elements, then you can, as a user input, define the crack spacing. Of course, then a good question is how to define it.
Yes? Yeah, of course.
But then you can use some simplified formulas. What we are finding is that usually it is not so critical if you make a small mistake in the crack spacing or on the results.
Yeah.
Yeah, bond failure, splitting of concrete cover.
Yeah, that's basically the mode for rapid bars.
Yes. Well, that's
just a detailed question, but not so critical.
That's you cannot obtain that bond splitting or that failures by splitting by this model that I discussed. Right?
Yeah, I think so. Yeah, I agree.
But in this model, you can take this into account because the way you can control that by your slip law.
Yeah, that's true.
Typically, in the way how you define your slip law, it takes into account that it is maybe close to the there is small cover, for instance.
Yeah.
So you can define the slip law, and there are some code formulas for the slip laws, depending on the confinement, cover depth, and so on.
Yeah. Okay,
So
thanks. Thank you.
that's how it can be done. And there is a question by Abdul Aziz. I'm interested to know the reference of the simulation method for reinforcement. Well, the reference, I don't know, if you are talking about this embedded reinforcement approach, I think it is pretty standard approach being used for, let's say, 30 years almost now. And I would have to, maybe you can write me an email and maybe I can find some original reference where it was used for the first time. But nowadays, I would say it's a basic, almost standard approach used by many finite element codes for reinforced concrete. All right, okay, so let me continue with my presentation. So this approach for reinforcement modeling, but also what I have mentioned before, these 1D, these beam elements and shell elements, this can be used to create very complicated models, which should be indicated by this this slide, which is a little bit simplified. But the idea is that for these areas around the columns where shear failure can be observed, we can use solid finite elements. Then for the rest of the plate, we can use shell elements. And for the columns, we can use beam elements, which would be, let's say, the most efficient way how to model such a structure. And in ATENA, we have all these elements. Here, these columns are modeled by so-called 3D beam elements. We now have also a possibility to model it as 1D beam elements. Similar situation is for the shells. Here you see these big elements in the middle. Those are actually shell elements, which on the outside look like solid elements. They have only displacement degrees of freedom. And this allows for an easy combination and connection to solid elements. Mansuri is asking, is there a library of historic earthquakes that can be used in a, yeah, if you mean whether there is some library of acceleograms in ATENA, it is not. It is not right. But you can import or include any earthquake accelerogram as a special file, and you can import that as a loading into ATENA. Okay, so let's go to the next one. Yeah, this is what I'm talking about. Yes, here we are using these 3D shell elements and 3D beam elements. And now in ATENA, in the recent versions, we also have a possibility to use more standard 2D shells and 1D beams, like you are, let's say, like you know from other software. Of course, you have to keep in mind that once you use these beam elements or shell elements, then you have to start using more traditional formulas for shear behavior and so on. So these elements cannot capture so well the shear failure. So that's why in many cases, when we are using ATENA for consulting projects, we use these combined approaches. The areas where we expect shear, we model that by solid elements. In the other areas, we can use successfully these elements which we know are good in bending, such as shells and beams. Let me now briefly mention also this durability model. I talked about that in more detail in the previous webinar. But nowadays, or the new model in ATENA allows that in addition to reinforcement modeling and all the other standard stuff, we can define special boundary conditions representing chloride environmental condition, carbonation. So it is defined as a condition on the surface, and then the program, because we know the location of each reinforcement bar, we can always determine the distance from this surface loaded by chloride. And we are using a one-dimensional diffusion model. I'm sorry, to estimate or to simulate the propagation of these chlorides or carbonation. And once the chlorides reach the reinforcement, we activate the corrosion model, which also depends, as you see in this example, there is a crack. So the corrosion here starts earlier because the diffusion in the crack is faster. And I'm sorry. And we can then simulate the reinforcement, the corrosion, and this mainly the main effect of the reinforcement corrosion is the reduction of the cross-sectional area. So this is then automatically taken into account. And I will show you one example where we applied it. So this was used now in some pilot projects in Czech Republic and Germany, where we developed a numerical model which was calibrated, as you can see here, by these trucks and by special laser then gauges, which were used to check the traffic. And based on that, we created a model where I will show here an example from from this calibration process, because this monitoring recorded the weight of the vehicles. So we then run many analyses passing the various weights, various vehicles with given weight on the bridge, and we match the response measured from the monitoring at the locations indicated here. So this is an example from such an analysis where the bridge is passing. Of course, the ATENA label on the truck is not the real one. Yes, this is just some advertisement that we put on model. And then we could make, after calibrating our model, we could make long-term predictions using this durability model. And here you see, for instance, this picture shows the corrosion levels after 100 years. So you could see 1 means almost fully corroded reinforcement, 0 means no corrosion. Of course, the reinforcement in the interior is not corroded, but that close to the surface is corroded more. Here above the support, there were cracks, so the corrosion was much larger. And here you see, let's say, the final collapse mode of this bridge. And this slide now, or these graphs, show what we did. So we simulated the life of the structure and the corrosion at various years. And then we always subjected the structure to some kind of virtual test to see its real load carrying capacity at various ages. So the blue curve is the original one. And then the gray one is after 50 years, the yellow one after 100 years, and the green one after 150 years. And then this is compared with the ULS load level, live load, and dead load. So then we could make some kind of reliability assessment, simulating the behavior of the bridge if we assume mean properties. That's the blue line, green line with the characteristic properties, and the yellow with if we apply some safety format. Currently, we are using the safety format from the FIB model code. And if you do that, then you see that the life expectancy is around 100 years, 110. Okay, so let me finish my presentation here, although I had some more examples here, but I think we should go to the program itself so that we have enough time to cover also this, this pre-stressing modeling I wanted to show you. And I see there is a question from Katap in regards to 2D modeling. How would you model an RC beam strengthened with FRP in order to capture the debonding? Well, yes, we do that, and in our in our installation we have also special tutorials for this. There is even a tutorial for this, or there is a YouTube video on this subject on our YouTube channel. So we can simulate the FRP strengthening also with also the debonding. So please have a look at that. Either if you have ATENA, you can look at that tutorial manual, or you can look at our YouTube channel. Vasilis, yeah, hello Vasilis. Does this chloride corrosion modeling provide a single static analysis? So does it require sequence of transport and static analysis? No, it is only in static analysis. So of course, in static analysis, normally we don't have a time. So there is a special way how when you apply this loading, you also give it a function how step relates to time. So of course you have to define some proper history, a loading history, but the answer is it is done within a static analysis. So there is no need to make another transport analysis, because we thought that there's no need to make a full 3D or 2D transport analysis if this chloride propagation, in most cases, it is a one-dimensional process. Usually it's just a distance of reinforcement from the concrete surface. Why to make a full 3D or 2D transport analysis? So we are using only one-dimensional transport analysis, and this can be done within the static analysis. Okay. Now let me discuss this problem of pre-stressing, yes, which is the topic of our webinar today. So now what you see on the screen is the GID program, which is the preprocessor we are using in ATENA for more complicated problems. It is a program from Spain, from Barcelona, and it is a nice program which is very inexpensive. So I think the price performance ratio is very good. And we are using it with ATENA for these more complex problems. This package, which is devoted to more complicated models, we called ATENA Science. So in this program, you model the structure by defining points, lines, and then you connect the lines to surfaces, to volumes, and finally to volumes to simulate 3D objects. So in this situation, if I turn off the individual layers, so we see we have a concrete with some supporting plates. This simulates a concrete beam. We have stirrups to capture shear, to increase the shear strength of this beam. And then we put some curved cable to simulate some pre-stressing. So now, if we can look at the individual materials which are assigned. So here are the various material properties. Of course, I have to turn off the concrete so that we can see how it is inside. Yeah, so we are using this cable 1 material. So let's have a look how this cable one material is defined. So I go to data here, materials, and it is a reinforcement material. So it will be under the group of reinforcement, and there is this material cable. So this material has a Young's modulus, has a characteristic strength of 1,500 MPa, and it is generated by some Eurocode classes, assuming design characteristics. So then we obtain this kind of design parameters. So here you can see, see also how this is defined in ATENA. You can define as many points of this stress strain diagram for reinforcement. In this situation, we are using only 2 points. That means 1 and 2. That after this 2, it is assumed that the reinforcement breaks. So there will be a drop down to 0. Now, however, we want to simulate that this cable will be pre-stressed. So we give it under the geometry tab, we give it a property that it is an internal cable. And then we have this bond behavior dialog, which says that this bar is okay. This is another example that I want to show another one, but that's okay. We already have this one. So maybe I open the other one. I want to show a situation. Sorry, I have 2 examples open here and I opened the wrong one. I wanted to show a situation when this cable is fixed on one side and pre-stressed only from one side. So in this case, we can look here at this again at this material properties, and we see then here that it is fixed at the end. Now to see where is the end, we look at the orientation, how this cable is defined. So this we do here by clicking the utility, swap normals, lines, and we can click this. Now we see that this line is defined in this direction by this little blue arrow. So that means this is the end and this is the beginning. So we are fixing this bar at this end, or this cable at this end, and we will be pre-stressing from this side. So the pre-stressing we see if we look at the loading. There we can see what are the loading conditions for lines. And there is a special pre-stressing condition for lines. And if we draw this condition, I see nothing. That's because I'm in the wrong interval. If I switch to the right interval, we will come to that later. I see that I have defined a pre-stressing of 1,000 megapascals, and it's applied at the beginning. So it's fixed here, and here we are applying the pre-stressing. And so we will have now in our loading history, we have to always think when making nonlinear analysis, what is the loading history? So in this case, we first apply pre-stressing. And then in the next interval, that's the second interval, which I was showing before. This second interval doesn't have the pre-stressing, but this second interval have a line load here at the top by this so-called universal load universal. Yes, draw colors. So we see that there is a universal loading. This is another new option in ATENA, that you can apply line loads independently of your model. So we have this line load, which will be then increased up to the peak load. And one more thing, I wanted to show you how this prestressing is applied. So I go back to the first interval where we have the prestressing applied. And I look at the prestressing for reinforcement line load. Okay, I'm sorry, I already mentioned that. This is the start node, 1000 MPa. So this is now clear. So let's summarize loading history. This is done in Git by this interval data. So in this situation, we have two intervals. One is interval with prestressing and dead load. And second interval is that we keep increasing this line load up to failure. So let's now create the mesh. So this is the automatic mesh generation. I'm using the structured mesh so that we can nicely have a nice uniform mesh for our model. So this is finite element mesh. If you look inside, you can see how the reinforcement is passing through there. We talked, or I told you before, that this reinforcement will be then in ATENA subdivided into small truss elements. So I will start the analysis and then I will answer the questions which are appearing there. So I will also check whether I'm running in ATENA Studio 64-bit version. And I can define, I want to use some parallel processing. In this case, I want to use the 6 processors on my computer. So I start the analysis. Tells me it is running. Okay, that's because I was trying it before you joined me. But let me close this. And I start it again from the beginning. So I start the analysis again. So let me go to your questions. As the analysis will be running. Maybe before going to the questions, let's just address what we see on the screen. So right now we are in this process of pre-stressing. Let me pause the analysis. So you can see that we are applying the pre-stressing on this left end. The right end is fixed. And because of the pre-stressing losses, we see kind of degradation or reduction, I'm sorry, of the stress in the reinforcement. And on this, okay, let me resume the analysis. Actually, we applied the pre-stressing in 2 steps. And now we are in the second interval where we are gradually increasing the load. So as it goes, I will answer some of the questions here. Dario Lamaza is asking, is there a possibility to have the Git file for the analysis of the bridge loaded with the moving track and the analysis of corrosion evolution? Well, of course, you can combine it, but we have to understand that the moving of the track is usually a fast process and the corrosion takes time. So you will have to define some proper history that you first maybe have a corrosion evolution with constant load representing maybe the dead load. This may run for several steps simulating this corrosion process. And then at the end of this of these corrosion steps, you can apply the track load by moving the track across the bridge. So this can be combined. But of course, you have to understand that it cannot be together, yes, because the corrosion is slow, the track is fast. So those are, let's say, different processes taking place at different times. Okay. Ansi, is it possible to take into account friction losses? Yes, yes. Well, I forgot to mention that, so maybe I will keep the analysis running in the background, and I forgot to show you the properties which are important. So if I go back now to the preprocessor and I open this material definition for this cable, actually I went quite quickly through it. We have these two cable properties defined, two cable materials. Because at the beginning, this cable is not injected, so it is the cable with this number 1. And here we have to define these friction properties. So we say that there will be this friction coefficient, which simulates the bond friction in the tendon pipes, mainly in these curved regions. And then we have the Vogel coefficient. So these friction losses are controlled by these two parameters. This friction coefficient, which mainly is in the areas where we have curvature, and the Vogel coefficient, which is mainly in the straight areas, which is mainly given by the, let's say, the fact that our prestressing pipes are not perfectly straight. So by these two parameters, you define the friction in this prestressing phase, and then we have this second model where we say it's also an internal cable, but in this case the cable is injected. Once the cable is injected, you see we have different properties here, and you can define some bond law. In this case, we use this CB FIB model code bond law, which you generate based on the concrete cubic strength and the properties of your reinforcement. Of course, in this case, it should not be ripped reinforcement. And here you say, so it should be maybe cold drawn wire or hot rolled bar, cold drawn wire probably. It is unconfined in this situation because it is close to the surface. And then you define the bond quality, which means whether it is corroded usually or not. Then you can generate this material. And what this generation does, it finds some bond strength, and it finds some, or it defines some bond law. So it defines some curve, bond slip curve. Alternatively, you have this table here, so you can define your own slip law. If you want to play with some special situations.
Okay, that's perfect. Thanks.
And what I forgot also to mention, or because we are a little bit running out of time, we have to say in the program that after the first interval, in the first interval, we simulate the prestressing. And in the second interval, we want the cable to be injected. So at this stage, we need to switch the reinforcement property. And this is done by a special condition here, which is applied to the tendon, where you can see here, it's a special condition on the tendon, which is applied in the second interval. And that's so-called activity conditions, which you can all, in ATENA, everything can be always deactivated or reactivated. So all elements, or it can be used for reinforcement, it can be used also for solid elements. You can always activate them or and then inactivate them. That means remove them from the model, and then later on maybe add them to the model with a different material. So that's what we are doing now here. We are after the prestressing phase, we say that we replace the bond model for this tendon. And sorry, where is it here? It's this. It's called reinforcement activity. Yeah, elements activity. Yes. If I do here, so reinforcement activity. I'm sorry. Here, reinforcement. So what happens here is that we activate this tendon with a new material, with a different bond properties, because now we want to simulate the fact that it is injected. So those are the two things that we have to do. We have to model first this prestressing phase and then change the material with a new bond law to simulate that it is injected with much higher bond strength than before. So let's go back to our problem, which was running in the background. Maybe let me interrupt the analysis now because we see we already reached the peak. Okay, so I interrupted the analysis and we can a little bit explore. Maybe we can go to post-processor now. And okay, so let's little bit see what happened here. So always in ATENA, it is good to define some monitoring points. Yes, in this case, we are monitoring the reactions, total reactions in this situation, in this beam, and the deflection in the middle. And you see here that first the displacement was going up. That's because of the pre-stressing. So if I go to this step, which was step 2, I can go back to this step. And at this point, if I increase the deformation, you see at this point, the beam is being lifted because of the pre-stressing. And here we are monitoring the total reactions. Don't be confused that we have some reactions. That's because at this first interval, we were applying the pre-stressing together with a dead load. That's why we obtain some reactions, because we take into account the weight of the beam as well. And here we see this pre-stressing losses. So you see that we are pre-stressing up to 1000 MPa. And at the other end, we have about 868, mainly due to these friction losses. And now we start increasing the load. I went back to some further steps when we can see also some cracks. So as we increase the load, of course, we see now that at the points where we obtain cracks, now we have some bending cracks. And then at those points, we also see that we have sudden increase in the stress in the tendon. If I go a little bit more, we have more cracks, larger crack opening, higher stress in the tendon. What is also now interesting to see that we can also look here at the slips in the tendon. So I can go here, and here we have various options how to display what's going on. So we can either display things as scalar on the reinforcement, or we can express results as evolution. The diagram, now it is the stress, but maybe interesting also to look at the slips. So you exactly see how the reinforcement tendon starts slipping, and you always see it's around the cracks. Yes, on one side of the crack, the slip is positive, on the other side is negative. We can also see what would be the bond stress. You could see the bond stress is always on one side it's positive, on the other side it's negative. So if we go now all the way to some, this is basically close to the peak, or actually at the peak, I think. We decrease the scaling quantity. So at this point, you see a lot of strains in the tendon. You see now the strain in the tendon, which is indicated by this color. So as I told you, we can, on the reinforcement, we can display things either as evolution. So this 1D evolution is showing the bond stress. And by color along the reinforcement, we are showing the strain. So we see that the strain in the reinforcement is more than 1%. So that means the reinforcement or the tendon is yielding. And that's in the middle where we have the highest crack. But on top window, we are looking now at the equivalent plastic strains, which is the best indication of crashing of concrete. And we see that this value is larger than the epsilon CP. That means the plastic strain at compressive strength. So we see that actually we are obtaining crushing of concrete and the yielding of reinforcement at the same time. So let me go back to the questions. Francesco is saying, with reference to the corrosion, discuss how does ATENA behave on stress corrosion? Yes, you are right. There is always stress. Corrosion depends on the stress and depend also on temperature. Well, this currently there is no dependence on stress in the model. You could, of course, take this into account by the proper, because there are some coefficients which drive the corrosion rate, especially when there is full cracking or spalling of reinforcement. So then you can really, this is an input parameter, the corrosion rate. And this, then you can define according, taking into account by considering the fact that you have reinforcement under high stress, you can take this into account. But currently, the corrosion model specifically does not consider stress. Suggestion on Giuseppe on external cables modeling. Yes, it is very similar, except in external cables, you have the friction only at the deviators. And this can be done in ATENA. Actually, there is, if you look at this material definition for the 1D reinforcement, there is a possibility to select either normal reinforcement, bar with bond, or cable. By that we mean external cable. There is an internal cable. So by this cable option, if you select that, you will notice that again you have to define where is the active anchor, and you have to define the friction. This is the friction and the deviators. You can also define the cohesion there, but this usually I think is 0. But the friction and the radius of the deviator, these are the important parameters that can then be used to simulate the pre-stressing losses in the same way as we did it here during the pre-stressing. And in these cables, external cables, usually you don't have the second phase that it is injected. So you won't need to make this exchange of material. You could keep the same material definition for the whole analysis process, because you will have friction or slips in these deviators even during the loading. Yes, I think some people have to leave the webinar, which was originally announced for 1 hour. So I would like to keep to that also, but Pavel Ostrovsky has one more question. How is it possible to account flexure stiffness of bar? Is the only way to model reinforcement bar with solid finite element? There are verification of such modeling approach based on any experiments. Well, actually now, and with this version 5.7, it is, you remember I told you that we have the possibility to use one-dimensional bar, one-dimensional beam elements. So it is possible to use these beam elements also to simulate this embedded reinforcement. And we are preparing, or I think even in the current installation of version 5.7, there are examples how to do that. And my colleague Mohammed is also preparing the YouTube presentation, YouTube tutorial on this. So that means you can use these beam elements also as this embedded, with this embedded approach. Yes. So I think I would like to finish or conclude this webinar today. I thank you very much for your presence and listening and interest in ATENA. I hope you will try this new version. Right now it is, we are almost ready to release it, and it is already available for trying and testing on our website. But before downloading it, please make sure that you have a valid maintenance. I wouldn't like you to run into some problems that you install it and then you find out that it is not working for you. So also many thanks to you, and we will also have this webinar available, this recording, for you to look at it again if you need to look at some of the points once more. So thank you again, and I will now conclude, stop sharing my screen, and I'm also stopping.
ATENA program produced by Chervenka company. You can find us via the website and download the program from it, or on YouTube by name Chervenka Consulting, or in Facebook by name ATENA. Finally, we thank you for your attention, and for any inquiries, please don't hesitate to contact us. Have a nice day. Bye bye.